All right, good morning, everybody. Today we'll be talking about moment of inertia, torque, and angular momentum. Okay, we have been looking at the rotational motion in the previous lecture, and we tried to relate the linear quantities to your rotational analogues. Okay, and today we want to start off by looking at the kinetic energy of a rotating disk. Okay, so the question we are going to ask ourselves is, what is the amount of kinetic energy that is stored in a rotating disk of mass m? Okay, so let's define this disk as having the angular speed as omega. Okay, and let's say that the disk is rotating along this axis O, and we can all visualize that this axis is coming out of this plane of the screen. We can try to find the kinetic energy of a small mass element that is rotating in this disk. Okay, so let's take a small mass element here. Okay, and let's say this small mass element has mass mi. Okay, and it is located at position r of I from this axis of rotation. Okay, so this is your axis of rotation. All right, so if I want to find the kinetic energy of this small element I, okay, I know that it is 1/2 times the mass of the element, and let's say it is rotating with some velocity v of I, and it will be 1/2 mi vi square. Okay, and from our previous lecture we know that we can express the velocity in terms of omega. Okay, and vi is just omega times ri. Okay, and then we have to do a complete square. Okay, and the reason again why we want to write omega is, if you look at any mass element that is present in this disk, okay, all of them have the same value of omega. Okay, however, they will have different values of vi. Remember, if there is a mass element, let's say located at a position here, okay, this value for v of j for this mass element here j is different than this vi. Okay, but they both have the same omega. Okay, and so we can simplify it and write it in this term: 1/2, you get omega square, and you have mi times ri square. Okay, so now I have the kinetic energy of a single element. So if I want to find the kinetic energy of the total disk, then I can just sum over this mass element, and so that I get the total mass of the disk. And so I will get the kinetic energy total, that is of the disk, will be the summation of this term, which is 1/2 omega square mi ri square. Okay, and my omega is a constant term, so it can come outside, and then I get summation of mi ri square. Okay, and this term that you are getting, which is your summation of mi ri square, this term is known as your moment of inertia. Okay, and so we can write that the kinetic energy of the disk is of the form, we have 1/2 I omega square. Okay, and remember previously we had kinetic energy is 1/2 mv square. So now instead of v we have omega, and instead of mass we have I, which is your moment of inertia. Okay, and again, what is this moment of inertia telling us? Okay, so remember from a discussion earlier, inertial mass, it is the property of a matter that is resisting your motion. Okay, so if for example, if a body has a large inertial mass, we say that it will have more resistance to motion. Okay, and if a body has low inertial mass, then it has less resistance to motion. Okay, now similarly, I is your resistance to your rotational motion. You can understand it by saying that a body that is free to rotate about an axis, it opposes any change in its state of rest or rotational motion. Okay, and that is what we are defining as your moment of inertia. For different objects, this moment of inertia will depend on the axis of rotation. For example, you have a cylinder and it is rotating about this axis that is going through the length, complete length of this cylinder, and so you get 1/2 mr square. However, if you go and take an axis that is coming out from the side and going below the cylinder, then your I value completely changes to this expression here. Okay, so the moment of inertia, it depends on the particular axis of rotation that you choose. Okay, also it depends on the shape of the object. Okay, so if you have a cylinder, it will have a different moment of inertia, and if you have a solid sphere, it will have a different moment of inertia. Okay, so both of them have different shape, and so they will have different values of moment of inertia. We have looked at linear momentum before, and we defined linear momentum as a quantity p which is given by mass times velocity. Okay, and we said that linear momentum is a vector, and it has a direction, and the direction is pointing in the direction of the velocity vector. Okay, so you have an object here. If it is moving with some velocity like this, then your p is also pointing in the same direction, and it has a value of m times v. Okay, so that is your linear momentum. So now when we are defining angular momentum, again, it is important for us to choose the axis or the origin from which you are defining the value of angular momentum. Okay, so let's choose a point of origin here. Okay, and so if I want to find what is the angular momentum of this object, okay, so the angular momentum will be defined as L, and now we have to choose our origin that we are choosing. So let's define this L from this axis O. Okay, and it will be given by the product of your vector r, which is the position vector from this axis that we are choosing. So that is your r. Okay, so r cross your value of your p, which is the linear momentum. Okay, and this cross product, right, we can also write as r cross m times v. Okay, and again we know that m is constant, so it can come out. So you can again write this as m times r cross v. Okay, remember, cross product, you cannot interchange r cross v with v cross r. Okay, it's not the same value, so you have to remember that it is r cross v. Okay, and if I try to find the magnitude of this angular momentum, then the magnitude will just be m times r times v times the angle between them. So the angle between them is theta. We can define that. So that is your value of magnitude of your angular momentum. Again, the important thing to remember is that angular momentum, it depends on your choice of your axis. Okay, because suppose I had chosen my value of origin to lie along the same axis. Okay, suppose it was lying along the same point here. Okay, so now in this case, suppose this is my point q. Okay, so if I try to find L with respect to q, then my product of, let's say this is r of q, cross my value of v of the motion, right? Because the angle between them is 0, I will get the value of the angular momentum as 0. Okay, so angular momentum is not an intrinsic property of the system. Okay, so what is an intrinsic property? An intrinsic property of the system is something that doesn't change, right? Suppose I'm asking you a melting point of aluminium. Okay, so that value of melting point doesn't change, it is fixed. Okay, so that is an intrinsic property of the material. Okay, so linear momentum, if an object is moving, it is an intrinsic property of the material. It doesn't depend on other factors. Okay, so however, angular momentum, it is not an intrinsic property. So you have to always define the axis and the origin from which you are calculating your value of angular momentum. SI units of angular momentum will be m is kilogram, R is meters, V is meter per second. So you will get kilogram meter square per second. Okay, so those are the SI units of angular momentum. Let's take an example of the Earth and the Sun system. Okay, so here you have the Sun. Okay, and here you have the Earth that is going around the Sun. Okay, and at any instant in the rotation of the Sun, it has certain velocity. Okay, so let's say the velocity is pointing in this direction at position A, and then the velocity is pointing in this direction at position B. Okay, now if I want to find the angular momentum of this system of Earth rotating around the Sun, then again I have to choose my axis. Okay, so let me choose this center as my axis. Okay, so let me choose this point here. Okay, so I want to find L with respect to C. Okay, so that would be M times my cross product of R. So I have to define this radius, okay, from this point C of the Earth cross with the velocity with which this Earth is moving. Okay, so that is this value right here. Okay, and by good approximation, this angle is always 90 degree. Okay, so if I want to find the magnitude, what I will get is L of C is M times R times V. Okay, so that is my value because sine of 90 is 1. Okay, so at position A, I get my value is M times R times V. Okay, and similarly, if I want to find at position B, so L of C at position B will again be M times R times V. Okay, why? Because again this angle is again 90 degree. Okay, so we have a situation here where your velocity is changing all the time. Okay, however, your angular momentum is not changing. Okay, and what does that mean? If angular momentum is not changing, that means that angular momentum is conserved. Okay, so just like what we were talking before, that linear momentum can be conserved, similarly there is the idea of conservation of angular momentum, and it of course depends on your axis that you're choosing for your origin or the axis of rotation through which you're considering. Okay, and so we have defined angular momentum L as being the cross product between your position vector about some point times your linear momentum vector. Okay, and if I look at this change in angular momentum now, which is dl by dt. Okay, so if I want to take the derivative, that would be drq by dt cross p plus I will get r of q cross dp by dt. That is just the expression of taking the derivative on the right hand side. Okay, now if an object is moving, dr by dt is just your value of velocity, right? Dr by dt is just v. So you are getting v cross p as your first term, and the second term is r of q times dp by dt is nothing but force, right? Change in momentum is what is the force that is applied. Okay, so we know that dl by dt will be equal to this term, right? However, we know that v and p are pointing in the same direction, so the cross product for them has to be 0. Okay, so that means we are end up with just the term that dl by dt, the change in the angular momentum is given by this quantity which is called r cross f. Okay, and this quantity is what we are defining as torque. So let's say there is no torque acting on the system. That means dl by dt is 0. Okay, or torque is 0. So if there is no torque acting on the system, then what is happening? This term is not changing. Okay, so that means angular momentum is conserved. Along these lines, now let's think again about this rotating disk. Okay, and now what I'm going to do is I'm going to rotate this disk about this center of mass. Okay, so we know for this disk the center of mass is going to be somewhere here. Okay, now I'm going to create a rotation about this center of mass. Okay, and let's say that this disk is rotating with a value of omega. Okay, and now I want to find what is the angular momentum of this disk. Okay, so I want to find the angular momentum of this disk. All right, so I have to define this point. So let me take this point as point C. Okay, so I want to find L with respect to C. Okay, remember we always have to do that because L will depend on where you're calculating it from, right? Because the factor of R is the distance of the measured from this point C. Okay, so again I will take a small mass element here. Okay, and I will define the small mass element as Mi. Okay, and I will say the angular momentum of the small mass element Mi, okay, will be nothing but Mi times the position of this mass element from this position of origin, that is defined as Ri, and I will take the cross product with your value of the velocity with which this mass element is moving, which is, let's say it is Vi. Okay, and again, for any point that I'm considering from the center, the value is 90 degree. Okay, so if I look at the magnitude of this term, I will simply get Mi times Ri times V of I. Okay, because the angle, again, sine of 90 will be 1. Okay, but again, I know that Vi is given by omega times R of I. Okay, so then my angular momentum for the small mass element will be m of I times omega times Ri square. Okay, so now if again I want to find the L of the disk, all I have to do is I have to sum over all of this mass elements Mi. Okay, and that would mean I am summing over all of these values of Mi omega Ri square, where I will go from whatever value to the whole mass. Okay, and again omega is constant, and so I get summation of Mi Ri square. But we know that this term Mi Ri square is your moment of inertia. Okay, so your L, which is your angular momentum, is related to the moment of inertia by this quantity I times omega. This L is about the center C, and I is also about this center C. Okay, and so this is a generalized statement for objects that are rotating about the center of mass. This angular momentum is an intrinsic value, and it does not matter on where you're choosing this origin from. Okay, so you can have chosen anywhere whatever value you had here, right? You will always get that the value for your angular momentum, as long as this object is rotating about this center of mass, the value of angular momentum will be the same. Two more terms. One of them is the mass. Mass is related to your I, which is your moment of inertia. It is a one-to-one analog. Same, it is causing resistance to rotational motion. And you had force when you were doing translational motion, and now you have torque when you're doing rotational motion. Okay, so if you are considering rotational motion, you can rewrite the Newton's laws in terms of thinking about torque, right? That the first law would read something like this: that a rotating body will continue to rotate at a constant angular velocity unless an external torque acts on it. Okay, so only if you have an external torque acting on it, it will change the motion that it is doing, or else it will keep going with the same angular velocity. Okay, so that would be your first law, and we can define the second law very close to this first law, right? So you have your term for your torque as R cross F, right? So here, if you look at the relationship, right, F we know is M times A, right? And for something going in circular motion, A is R times alpha. Okay, so you can rewrite this torque as M times R times alpha times another R, so you get mr square alpha. Okay, and this mr square term is your moment of inertia. Okay, so torque can be written in the terms of I times alpha. Okay, and this is very similar expression. You see, you had force is mass times acceleration, but now you're getting torque is moment of inertia times your angular acceleration. Okay, and that is your expression for the Newton's second law when you're considering rotational motion. Some of you might be aware of the Chandra X-ray observatory. Okay, so of course it is named after the great scientist Subramanian Chandrasekhar, and he did a lot of his seminal work on astrophysics. And in 1983, he won the Nobel Prize in Physics as well. Okay, when we want to see the emission from stars, from planets, and we want to answer a lot of questions about the universe, whether what is the age of these objects in the sky, what is the age of the universe. We wanted to know why is the universe expanding, why is the universe cooling down, and what is the composition of these planets. Is their life sustainable on other planets? So all those things, they need to be observed, and it is very difficult to do that from Earth. Okay, because we have our atmosphere, and a lot of emissions that are coming from these stars and planets, they get absorbed by the atmosphere. Okay, so if you are on Earth and you're trying to point a camera towards your sky, you will not be able to get the complete picture of what is happening. Okay, so back in 1999, uh, the Chandra X-ray observatory was launched. Okay, from the Columbia shuttle. All right, and what you're seeing here is the trajectory that this observatory does. Okay, that you're seeing, this is the trajectory of the Chandra X-ray observatory. All right, so uh, it is going almost 133,000 kilometers away from the Earth, and then it comes close to the Earth at one of these positions. Okay, and what it's able to do is it is able to go beyond this radiation belt, okay, which is the van belt, and it is able to observe a lot of emissions that are coming from these objects in space. All right, and you can guess from the name itself that what this Chandra observatory is doing is it is looking at X-ray emissions from the objects. Okay, so this is the design of the Chandra X-ray observatory. It's fairly straightforward. You have the solar arrays that power it, and you have a bunch of mirrors that basically can take light and focus it on this CCD detector. Okay, and the CCD detector is basically grabbing all the photographs. Okay, now in the beginning, a star is just a part of this hydrogen dust and cloud. Okay, now as gravity is attracting these cloud together, eventually this gas and this dust, they compress. Okay, and slowly they start rotating. Okay, and what happens is when they start rotating, you can see that all these gases and all these particles, they are drawn together by this gravitational forces. Okay, and they get more and more compressed, and then of course a pressure develops from this gas, because later on you will learn about this. It's called electron degeneracy pressure. Eventually what happens is there is to be a stable equilibrium has to be developed, where the pressure gets balanced by the gravitational force that the stars are experiencing. Okay, and slowly and steadily this compression happens, and these planets and this solar system gets formed. While this process is happening, there are a lot of emissions that are coming out of these planets and stars. Okay, because the environment that they're in, you have this hydrogen that is burning and it's getting converted into helium. Nuclear fusion is happening, and all these explosions are happening inside this stars. Like the sun, it's there constantly explosions are happening, and then the gravitational field is trying to contain this explosion that is happening. Okay, so during the life cycle, what happens is a star might get converted into different things, right? So now here where you might all have learned in school that the sun that we have is a red giant. Eventually, this nuclear fusion that is happening in the sun, it will eventually die down, right? And our sun will become this white dwarf. Okay. Now, what makes a planet become a red giant, and what makes a planet become a supernova or a neutron star or a black hole? Okay, and this is where Chandrasekhar's limit comes into picture. Okay, so Subramaniam Chandrasekhar, he uh, described a quantity which is known as the Chandrasekhar limit. Okay, that describes that if a mass of this progenitor star, if the mass is less than 1.4 times the mass of your sun. Okay, so this m with this dot, it describes the mass of sun in our solar system, which is about 2 times 10 raised to 30 kilograms. Okay, so for any star that is starting here with mass less than 1.4 times the mass of the sun, this will lead for the star to become a white dwarf. Okay, and this is known as the Chandrasekhar limit. Okay, and any star that has the mass of greater than 1.4 of this mass of the sun, what it will do is either it can become a supernova, right? And from the supernova, it will become either a black hole or it will become a neutron star. Okay, and that would depend on the original star. Okay, so black holes have much more mass, and that's why they have much more gravitational field. Anything that goes inside this black hole, it's very hard for it to escape. Even light, when it goes around the black hole, it won't be possible for it to escape, because there is so much of gravitational pull because of the so much of mass that is concentrated here. Okay, however, if you are somewhere in between the mass of the white dwarf and the black hole, you can get converted into a neutron star. Okay, and so these different life cycles of the star, they can be studied by these observatories that are present in the sky. Okay, and so what happens is you can imagine that when this star is getting formed, okay, and so you have this entire gas which is getting compressed because of the gravitational attraction between them, right? And what is happening here, your value of your radius of this cloud, right, is going down. Okay, so the radius is going down, that means what is happening, your I, okay, is going down. The moment of inertia is going down, because I is what? I is mr square. Okay, now if I is going down, we know that angular momentum is conserved. Okay, so if angular momentum is conserved and I is going down, that means to keep the L constant, omega has to increase, because L is I times omega. Okay, so if I goes down, omega has to increase so that L stays the same. Okay, so all these stars that are basically compressing, they start rotating, and the more they compress, they start rotating faster and faster, and they have this rotational kinetic energy. Okay, now while they are rotating, what happens is they have these emissions that they come out. So here you can see the emission coming from this supernova, which remnant, which is known as Crab Nebula. Okay, it was discovered around 1731, and this is now photographed using the Chandra observatory. Okay, so this emission is coming especially because this rotation is slowing down. Okay, so every day this rotational kinetic energy of the star is reduced by certain amount, and that amount that the energy is reduced is released from the star in form of emission, and that emission is what we see with your Chandra X-ray observatory. Okay, and again, from this emission we are able to find out what is the temperature of this supernova, what is the composition, and all those things can be studied. Okay, and it is quite interesting to see, we have a lot of different observatories in the sky. Okay, you might have heard about the Hubble telescope, The Hubble telescope gives us images in the optical region, in the UV region. You have gamma ray telescopes are available. You have Chandra X-ray observatory. Okay, and so all the images that you're seeing here are from the same remnant of the supernova. Okay, but these are different images. One is the radio wave image, one is the infrared image, one is the optical image, and you have the UV image and you have the X-ray image coming from Chandra. Okay, so they have all superimposed here, and they form the entire emission that is coming out from this leftover of this star. Okay, if you have interest in astrophysics, you have to be good in optics, because as you can imagine, a lot of these things have to do with working with light, working with electromagnetic radiation, and you need to have a good knowledge about working with optical components, how these mirrors are made, how detectors work. India is doing so well in terms of the work that is it is doing in the space program. And now recently we launched our own observatory satellite, which is the gamma ray satellite, I believe, and there is plans of upgrading that system as well. Of course, we have the International Space Station, where some of these detectors, basically they are just cameras. They are just clicking photos of different planets, and they are looking at light that is coming from the planet, or electromagnetic radiation that is coming from the planet. Okay, and a lot of interesting things happen when you're looking at this electromagnetic radiation that is traveling through space, because you have things interacting with each other. You can imagine, suppose you have X-ray emission that is coming to the observatory, and you're trying to take a picture, and then suddenly there is a planet that comes in between this emission. So depending on the atmosphere of the planet that interacts with the X-ray emission, it will tell you what kind of atmosphere the planet has, right? If all the X-ray goes through the planet, then the atmosphere of the planet is not interacting with the X-rays. However, if the X-ray emission that you're recording from a star suddenly gets affected by a planet that is in between you and the planet that is emitting the X-ray, and then it can tell you about the atmosphere of the planet. It can tell you how much size of the atmosphere it is. Is it 100 kilometers, 200 kilometers? All these things can be figured out. Okay, you know, there are so many things about the universe we are still trying to answer. Right? There are so many missions that are still planned. NASA is launching a mission next year. And again, I think they are sending another observatory up in the sky. It's called the James Webb telescope. They are sending it up. So I think it's supposed to replace the Hubble telescope, and it has a higher trajectory. So we will be able to image objects much farther than what we have ever imaged before. There is still search for you know, planets that are containing water and life. There is still work to be done on that aspect. The recent launch that happened for India was partly successful. We were not able to land the rover. However, we still had uh, the the trajectory map, so that was some progress we did on that front. So of course that was a very ambitious mission by India itself, because that part of the moon itself is not explored yet, right? So there, it's called the dark side of the moon, right? There is even a movie about the dark side of the moon, right? Transformers. So the way the moon rotates and the earth is rotating about the axis, we cannot see a part of the moon, and it is always not visible to us from earth. Okay, so this the movement of the moon and the rotation of the earth is synchronized in such a manner. Okay, our plan was to finally go and see the dark side of the moon and look at the ice deposits that are now available on moon, right? So we have already found that there is ice deposit there. So a lot of things are yet to be explored, and India is doing very well. There are a lot of opportunities for students of PCM to work in ISRO. They are coming up with positions every year, and they have their separate examination. You can go to their website and see. Okay, so it will be surely be wonderful if at least some of you end up choosing that as your career.